Okay, so we are ready to start. Today is a pleasure to have in our colloquium Carlo Cannarozzo. So he studied at the Bologna University, as he said. He just defended actually on May 24 under the advice of Carlo Nipoti and Alessandro Sonnenfeld. So he works mainly on the evolution of early type galaxies by studying the evolution of the stellar mass velocity dispersion relation in early type galaxies. He also has been collaborated a lot with the people in the University of California in Santa Cruz with Alexei Leto and Kevin Bondi. And they've been they've been doing an analysis of the radial distribution of the stellar properties, such as the age, metallicity, and velocity dispersion of early type galaxies, comparing MANGA, the SDSS survey that everybody knows that we are also working here, by comparing observations of MANGA and the Lustris TNG simulation. So basically, he's like an interface between observations and simulations. And he has been also awarded with the Maria Slodowska-Curie grant in data science and machine learning to carry out the projects with Alexei Leto, but to train in a model based on simulated galaxies of the Lustris TNG and exploiting machine learning algorithms. Okay, so I hope that I say everything that I need to say. And it's all yours. So please go ahead, Carlo.
Okay, share my screen. Do you see my screen?
Yes.
And my laser pointer. Yeah, just a moment. Oh, sorry. Oh, sorry.
Yeah, we lost it.
We lost the presentation.
Okay. Okay, do you see now?
Mm-hmm.
Okay. Okay, I start. Thanks, Aldo, for the nice presentation. Again, hi to everyone. I am Carlo Cannarozzo, and I go to my PhD in astrophysics on May 24 at the alma mater studiorum Università di Bologna, working with Carlo Nipoti, Dr. Alessandro Sonnenfeld from the University of Leiden in the Netherlands, and with a great collaboration with Alexei Leto, Kevin Bondi, and all the other researchers here, listed here below, at the University of Santa Cruz in California, that I visited during my PhD 3 times for more than 8 months. And today I'm going to illustrate you 3 different projects I'm involved in the context of early type galaxies, the emergent-driven evolution, and the connection between galaxies and the dark matter halos. The structure of this presentation is the following. After an initial brief introduction that provide an overview about early type galaxies, their formation and evolution, and the physical properties, I go through the details of the 3 different projects, and then I'll sum up everything in my conclusion, and I leave you with my take-home messages of these works. Let's start. The first key ingredient we need for forming a galaxy is definitely the dark matter. We know from the lambda CDM model that after the Big Bang, from an homogeneous distribution, dark matter started to collapse under its own gravity into a scaffolding of clamps and filaments that we know as cosmic web. At the center of these dark matter densities called dark matter halos, baryons started to migrate, aggregating to gas clouds, and these gas clouds cooling down their temperature, collapsing, give the birth to the first generations of stars. And here we have the first generation of galaxies, proto-galaxies, that have a large amount of cold gas, but that also accrete from the surrounding cold gas inflows that feed both the galaxy that form new stars, new generation of stars, and feed also the central supermassive black hole. During its life, a galaxy may experience several galaxy merging that can dramatically change their internal physical properties and can trigger also new star formation episodes. Another key protagonist in this movie is definitely the central supermassive black hole, that through its radiation, it is capable to blow out part of the gas, causing a halt in the star formation activity. And once all this gas reservoir is exhausted, we end up with a system that basically experiences a passive evolution. And the only way to change internal properties is to interact with the environment and interact with other galaxies through mergers. The entire scenario that I've just described you is very long, and it may take giga and giga years, even more than 10 giga years, at the end of which we end up with an early type galaxies. The important thing that should be underlined in this very complex chain of events is that there are, during these giga years, tens and tens and tens of physical properties that coact together for forming and letting evolve these galaxies. Morphologically speaking, as you can see from this photo, early type galaxies are very simple system in the sense that they are characterized by a roundish or elliptical shape. On the bottom left panel here, you have a color mass diagram drawn from Shavitsky et al. 2014, populated by both late and early type galaxies. And although both kind of population are spread over the entire range in mass and over the entire range in colors, early type galaxies tend to occupy the reddest part of these plots. And also early type galaxies tend to be the most massive systems, as you can see here. The fact that ETGs are characterized by this red stellar population can be explained in terms of these two other results here. Here, as a function of the stellar mass, you have on the top panel the stellar metallicity, and on the bottom panel the age of the stellar population. And what is it found for early type galaxies is that this kind of galaxies, on average, are characterized by very metal-rich stellar population and old stellar population. And these results are, of course, corroborated from the state-of-the-art and more recent observation occurred with the Manga survey. For instance, these are the same plots of before. As a function of stellar mass, you have the metallicity and the age from Laserne et al. 2020. And regardless of the separation, the disentangle that the authors applied in ETGs to classify them as classical, elliptical, recently quenched elliptical, or other kind of subclasses, what should be underlined is again that this kind of system are composed by stars with a very metal-rich content and old stellar population. Historically, we know that early type galaxies obey some scaling relations. In the 70s, was found that the first two were the Faber-Jackson and the Corman scaling relations that link the luminosity, or equivalently, the stellar mass to the velocity dispersion and to the sides of the galaxy, respectively. And soon thereafter, in the 80s, it was discovered that these two relations are just two projections of a more general relation that is called fundamental plane, where all early type galaxies lie. At the beginning of this introduction, I show you that the process for forming and evolving a galaxy is very, very, very complex. But the stellar mass assembly history behind an early type galaxy can be easily summarized assuming the so-called two-phase formation scenario proposed by Oser et al. In 2010. In this sketch here, we have as a function of redshift, the stellar mass at given redshift relative to the mass at redshift 0. In the first stage of its life, an early type galaxy is mainly composed by the so-called in situ stellar component, so the fraction of star that was formed in that galaxy. However, as a consequence of galaxy accretion processes and minor and major mergers, the most dominant component from redshift 2, more or less, up to the present-day universe, that can reach even 70, 80, 90% in some cases of the total stellar amount, is the ex situ stellar component. So the fraction of stars formed in another galaxies and then accreted through mergers and accretion processes onto the main progenitor. And there are many features that suggest this merger-driven evolution behind early type galaxies. And this is, for instance, one of the study that we conducted in collaboration with Carlo Nipoti and other co-authors, where we studied the effect of dry mergers, both minor and major merger in binary systems, on the radial distribution of the so-called effective initial mass function parameter. Here, basically the effective IMF is the ratio between the stellar mass to light ratio observed in real galaxies or assigned to simulated galaxies relative to the mass to light ratio expected assuming an initial mass function assumed as a reference, for instance, as salpeter 1. We analyzed a set of these binary minor and major simulation with different orbital parameters, and we analyzed the radial distribution of the effective IMF, finding that, with respect to the radial distribution of the main progenitor here traced by the red curve, the final remnant, regardless of the mass of the two galaxy progenitors and the orbital parameters involved during the merger, the final galaxy, the galaxy remnant, always show a flattening in the innermost region. And this is an unequivocal signature of this merger-driven evolution because it's telling us that the two stellar components of the two progenitors are well mixed even in the innermost regions. Okay, so let's move to the first project of this presentation that is about the first systematic study in literature that provides a description and a question for how the stellar mass velocity dispersion relation evolved through cosmic time. As I showed you before, early type galaxies obey scaling relation. And with the improvement of surveys and telescopes, we are able to observe galaxies deeper and deeper in the universe. And we can study if these relations are still there at higher redshift, and if this relation evolves with the redshift too. And for instance, this is what was done for the size-mass relation by Van der Velde et al. In 2014 for a sample of both late and early type galaxies. Here we have 6 redshift beams between redshift 0 and redshift 3. And what is it found is that at fixed stellar mass, galaxy in the present day universe appear to be tend to be larger than their counterpart with the same mass at higher redshift. So in principle, one can think to study in an analogous way the evolution of the stellar mass velocity dispersion relation if it evolves. In this case, I drawn 2 redshift references of this relation at Z2, that is a redshift higher than Z1. If I put an early type galaxy at Z2 and I allow it to evolve to reach the functional form at Z1, these galaxies, supposing that it increases as a function of time its stellar mass, can reach the functional form at Z1 in 3 different ways. Maybe slightly increasing its velocity dispersion, maintaining more or less the same, or decreasing its value. In collaboration with Alessandro Sonnenfeld and Carlo Nipoti, we built a Bayesian hierarchical approach to study how the stellar mass velocity dispersion relation evolves through cosmic time. The problem here is that, unfortunately, unlikely was done for Van der Velde et al. For the size-mass relation that evolves through cosmic time. So far, there are no available survey that covers a so huge range in redshift with reliable and consistent velocity dispersion measurements. So the first complication of this work was to build my own sample that is composed by early type galaxies with a stellar mass greater than 10 to the 10.5 solar masses, covering the range between 0 and 2.5. Here you can see the redshift and the stellar mass distribution of the various subsamples composing my total sample. And there are 2 main subsamples. The fiducial sample up to redshift 1 consists of SDSS and legacy galaxies that were selected as early type galaxies, applying a selection on the equivalent width of oxygen second. And then I applied a one-by-one visual inspection, basically to remove all galaxies that in their images showing with features, merging in acts, spiral halves, basically just to keep a sample composed by a roundish or elliptical shape. And then I extended my sample towards a higher redshift, including looking for other works in literature that define in a similar way the early type galaxies and the definition of stellar masses. And if I collect all my galaxies and I put them on the stellar mass velocity dispersion plane, and I colored them all as a function of their redshift, what I define is this distribution. And as you can see, there is a very clear trend of the clear evidence that there is a trend, there is a clear evolution of this relation. And in particular, at fixed stellar mass, the higher the redshift, so redder colors here, the higher the velocity dispersion. As I've already said, I've modeled this scaling relation employing a Bayesian hierarchical approach that can be easily summarized in two main steps. The first step consists of fitting the galaxy sample in the present-day universe, that in my case would be the fit of the SDSS galaxies. From this fit, we get the normalization of the relation, the slope, and thanks to the Bayesian hierarchical approach, you are able also to account for the intrinsic scatter that is usually a quantity that is neglected in the fitting in literature. And then so we get all these hyperparameters, we put in my machine, and then I feed the rest of the sample, we assuming two different classes of models. The first class of models is the constant slope model, and as you can see here, is basically a model for which the relation evolves just in normalization. The other family of models are the evolving slope models, for which both the normalization and the slope evolves as a function of time. In any case, for each model, we consider other two models, allowing or not for the evolution of the intrinsic scatter with redshift. So at the end, we end up with a plethora of models. And according to the analysis of the Bayesian evidence of each model, we do find that the two most representative models of the relation are these two. On the left-hand side, you have a constant slope model. On the right-hand side, you have an evolving slope model. For both relations, it is found that the intrinsic scatter here, indicated by this gray error bar, is found to remain constant at all redshift. Here, I drawn 5 redshift references between redshift 0 and redshift 2, from violet up to red colors. But let me stress again that with this Bayesian hierarchical approach, you are able to trace continuously over the entire range of stellar mass and over the entire range of redshift this relation. As you can see, there is evidence for the evolution of this relation, and to be a bit more quantitative, for instance, a galaxy of 10 to the 11 solar masses should be on average a velocity dispersion of around 160 kilometers per second that can reach even 270 kilometers per second, more or less, at redshift 2. However, understanding how a progenitor galaxy evolves from higher redshift to reach the functional form at redshift 0 is not trivial at all. But thanks to our sample of galaxies and our relations found, we can identify basically two possible regimes. Below 10 to the 11.5 solar masses, if I put a galaxy at redshift 1, it can evolve to reach the functional form at redshift 0 in 3 different ways, increasing, maintaining, or decreasing its velocity dispersion. However, this scenario is not still valid above 10 to the 11.5 solar masses, where instead a galaxy from redshift 1 to reach the functional form at redshift 0 must necessarily decrease its velocity dispersion. So in conclusion of this first project, I would like to say that we defined clear evidence of the evolution of the stellar mass velocity dispersion relation that I've modeled with a state-of-the-art Bayesian hierarchical approach. This evolution can be with a constant or also an evolving slope, but in any case, I define that the intrinsic scatter is found to be independent of redshift. What will be the next of this kind of study? For instance, I can apply my Bayesian hierarchical approach for conducting the analysis of the evolution of other scaling relations, like the stellar mass fundamental plane, and to have a more complete 360-degree view of how individual progenitor evolves through cosmic time over the stellar mass velocity dispersion plane. I plan to make a comparison between cosmological simulation like illustrious TNG in order to reconstruct for individual galaxies, individual progenitors, the evolutionary path and how they evolve through redshift. So I concluded with the first project, and I moved to the second one that is in collaboration with Alexis Liotho and the group of Santa Cruz, whose aim is to provide an interpretative scenario on how the present-day galaxies that we observe in the universe assembled during their secular history. The main problem when we observe a galaxy is that if we observe these galaxies and observe a given star inside or a given stellar population, I cannot directly say if that star or that stellar population was born in that galaxy or was accreted from other galaxies. And so you have to necessarily look to dynamical quantities or to quantities derived from, for instance, from spectra. And you can build like a model like the one adopted by Oyarzun et al. 2019, where the authors studied for a sample of early type galaxies in the Manga survey, the radial distribution of the stellar metallicity. And they define that the eye mass tail of this early type galaxy sample show a flattening in the outermost region. And they built an ad hoc model for explaining this flattening, and their explanation is due to the fact that the exitostellar component from other galaxies is accreted and remains in the outermost region of the systems. Another possible way to obtain to understand if a stellar population was born in situ ex situ or provide a scenario is the one that I adopted in this work that I'm going to submit very soon to monthly Gnosis Royal Astronomical Society journal, whose aim is to provide an interpretative scenario about the merger-driven evolution of present-day early-type galaxies in terms of in-situ and ex-situ stellar components. To do that, as I've already said, I make use of Manga and TNG. Of course, why them? I have not to tell you what Manga is, since you are largely involved in this survey, but basically Manga up to now is the largest survey in the present-day universe that mapped more than 10,000 galaxies that exploit the integral feed spectroscopy technique. What does it mean? It basically means that when you observe a given object, you are able to spatially resolve individual region inside this galaxy, and for each region, you are able to get all the information you need. Why TNG? TNG is the next generation of the original illustrious simulation suite. It is a magneto-hydrodynamical cosmological simulation that mines the galaxy formation evolution in a cosmological context. And this suite consists of 3 different simulation volumes. And for this comparison, I make use of illustrious TNG 100. We select our sample of ETGs applying these 2 sample criteria. We select all objects with a stellar mass greater than 10 to the 10.5 solar masses, and we select only those objects with colors G-R greater than 0.6. Here on the bottom left panel, there is the color mass diagram reporting both the manga galaxies, here indicated by the orange dots, and the 2D gray histogram on the background tracing the illustrious TNG sample. While on the right-hand side, you have the 1D distribution for both manga and TNG of the stellar masses. I have not much time to go into the detail of this kind of analysis, but the problem is that when you compare observation and simulation, it's not trivial at all. And so to understand if the results that I'm going to show you in the next slides are in some way biased by our selection, we tested, and our assumption, we tested different definition of early type galaxies. We tested different stellar masses for both manga and TNG galaxies, and we tested also different stellar mass beams built assuming different approaches. And let me say that, however, in any case, we do not find any significant difference assuming all the combination of these definition. So in the following, I'll show you the results for early type galaxies selected as in colors as I showed you before, assuming for manga galaxies the dusty mass from Mert et al. 2015, while for TNG galaxies I show you the mass, I use the mass enclosed in a circle with an area enclosed within 2 half mass radii, and I compared the radial profile of the physical properties analyzed at fixed stellar mass beams. The 4 stellar properties analyzed here are the following: the stellar mass surface density, the stellar metallicity, age, and velocity dispersion. Concerning manga, we derived these 4 properties in these 5 beams listed here, and in particular for mass, surface density, metallicity, and age, we made use of the estimates made using Firefly and Prospector stellar fitting codes, while concerning velocity dispersion, we use the PPXF estimate. We drawn from the simulation the same stellar properties, but in simulation we are able to disentangle the role of the in situ and ex situ stellar components, as you can see here. And for each of the 2 stellar components, we compute 2 kinds of profiles. The profiles directly derived from the 2D projected map of the original maps, and the profiles from the 2D projected maps that were previously convolved with the manga PSF. And so let's start with the results. These are how the stellar mass surface density profiles appears. Let me explain how I will show you these results. Here we have 3 stellar mass beams, 10.5, 11, 11, 11.5, and above 10 to 11.5. The bottom panel shows you the direct comparison between the total stellar population in TNG and the manga estimates for the given stellar property analyzed, while below regard only illustrious TNG galaxies, where I disentangle the role of the in situ and ex situ stellar component. Let's focus on the 3 upper panels. As you can see, the illustrious TNG profiles remarkably well reproduce the radial distribution of both Firefly and Prospector estimates for manga galaxies at all radii and at all stellar mass beams. And this is a very good thing, because in this sense we can exploit, as we will see later, illustrious TNG for providing an interpretative scenario of how this kind of galaxies in the real universe are assembled through the cosmic history. What about the role of in situ and ex situ component? Here we can identify 2 different regimes. Indeed, below 10 to the 11 solar masses, the in situ stellar component, here traced by the red dashed curve, below 10 to the 11 solar masses is dominating out to 20-30 kiloparsec. However, going above 10 to the 11 solar masses, what is it found is that the ex situ component, so the blue dotted curves, becomes as relevant as the in situ component, or even more relevant than the in situ component in the very massive systems. And this fact, and the fact that the shape of the profiles above 10 to the 11 solar masses for both in situ and ex situ stellar components are very similar to each other, are two particular signatures of a stellar mass assembly history that should be marked by major mergers. But we will come on these later. Let's analyze other physical properties. These are, for instance, the stellar metallicity profiles. As we can see, more or less, TNG is providing a good representation in terms of the shape, the radial distribution of the manga galaxies, in particular above 10 to the 11 solar masses. What about the role of the ex situ component? What we define in TNG is that the ex situ component tend to be metal-rich, and in particular in the most massive systems, they tend to be systematically more rich than the in situ counterpart. Let's move on the stellar age. And here, as you can see, there is a very clear criticism between the two manga estimates, because as you can see, there is a systematic shift of 2, 3, even 3 gigayears assigned by Firefly Prospector to the same galaxies. As argued by Conroy in 2013, for instance, the fact that these two stellar population, these two stellar age estimates differ so much can be addressed to the fact that we are using two stellar fitting codes, and these two stellar fitting codes assume different input, different libraries, different fitting methods. But at least the good thing here is that the flat profile, the almost flat profile of illustrious TNG galaxies, more or less always lie in between the two manga estimates. What about the role of the ex situ component in this case? The ex situ component show more or less flat profiles, and these plots are telling us that the ex situ stellar fraction is systematically older than 8.5 gigayears at all masses. But we did more, and for instance, we analyze also the role of central and satellite galaxies. For manga, we disentangled the two stellar population using the Young et al. 2007 catalog here. And for TNG, instead, you are able to divide a central and satellite galaxy directly from the simulation. What I defined is that there is a significant difference between central and satellites and between the estimates of manga and TNG for the stellar mass surface density, metallicity, and age profiles. But so far, I haven't shown you the radial distribution of velocity dispersion yet. And this is how, and this is why I show you now the radial distribution of velocity dispersion. Let me explain, because this plot is a bit different with respect to the other that I've shown you here. Here we have two curves. The black and the gray curves are tracing respectively the role of central and satellite galaxies in TNGs. In TNG simulation, while the dots, the violet and orange dots, are tracing the median profile for central and satellite galaxies in the manga sample, respectively. What we define is that, qualitatively speaking, below 10 to the 11.5 solar masses, both the central and satellite median profiles for the simulated galaxies more or less reproduce quite well the radial distribution of the velocity dispersion for centrals and satellites in manga. However, it's not still true above 10 to the 11.5 solar masses. As you can see here, indeed, the median profile of satellite in TNG within the uncertainty reproduce well the radial distribution of velocity dispersion of both central and satellites. While the profile of central galaxies in TNG is systematically shifted up of a factor of around 50 kilometers per second. And the reason for this systematical shift is due to what argued by Lowell et al. In 2018, because central galaxies in illustrious TNG galaxies, in particular the very most massive galaxies, above 10 to the 11.5, for instance, have too much high content of dark matter. And this is the main responsible of this systematic shift. Overall, so far I defined an enough good agreement between TNG and manga galaxies, and in particular, TNG, as I showed you before, reproduce very, very, very well the radial distribution of the stellar mass surface density profiles of manga galaxies. So I can exploit the merger history of illustrious TNG to provide an interpretative scenario of present-day universe ETGs and how they assembled. Here, in these three mass beams, I show you three violin plots that show the distribution of the fraction of the ex-situ accreted on these systems. As you can see, as the mass goes up, the fraction of the ex-situ goes up as well. And in particular, for the most massive system, on average, more or less 80% of the total fraction is due to the ex-situ component. But how this ex-situ component is accreted? If I, for instance, analyze the fraction of the ex-situ component due only to major mergers relative to the fraction of ex-situ component due to all the ex-situ component, although these distributions are very spread over the entire range of on the y-axis, what is it found for TNG galaxies is that above 10 to the 11 solar masses, on average, half of the total of the ex-situ stellar component come from major mergers. And so, given the good agreement between TNG and manga galaxies and these last results, a possible interpretative scenario for the present-day universe early type galaxies that we observed can be that above 10 to the 11 solar masses, this kind of system may be the results of a major merger-driven evolution. So in conclusion, I compared the galaxies simulated in TNG and observed in the manga galaxies in order to provide a scenario of how these galaxies assembled through cosmic time. We do find that TNG reproduced well some physical stellar properties of galaxies, in particular the stellar mass surface density. There are no relevant differences between centrals and satellites, except for the high mass tail for velocity dispersion in TNG galaxies. And so we provided this possible scenario of a merger-driven evolution for early type galaxies that we observe in the local universe. This work will be submitted very soon, but what the next of this kind of analysis? Of course, I'm going to extend the analysis analyzing other aspects, for instance, individual chemical abundances in TNG and the manga galaxies. I'm going to reconstruct in TNG galaxies the stellar mass assembly history of individual progenitors, and these can be directly compared with the global and local properties for manga galaxies, for instance, as those shown at the beginning from Lasserre et al. 2020. And then I'm going to use also the newest data from illustrious TNG 50 simulation that are characterized by a higher resolution quality of the data. And then let's reach to the final part of this presentation, changing a bit the topic. As Aldo said before, in 2019 I was awarded the Marie Curie grant from the European Commission to conduct a project in the context of data analysis and machine learning. And thanks to this grant, I visited for more than 6 months the University of California, Santa Cruz, working with Alexis Liotho and their group, and also collaborating with the Microsoft research teams. In the last decades, in the last years, astrophysics has been living the so-called big data era. Every day, indeed, astrophysicists and cosmologists have to face with an enormous amount of data of different nature coming at a very huge rate. And one, of course, of the main sources of this huge amount of data are the current and next generation of observation carried out, for instance, from these newest and upcoming telescopes. Machine learning and deep learning techniques are widely used in astrophysics for a wide variety of problems. For instance, for classifying objects like galaxies, stars, transients, exoplanets, for disentangle dynamical aspects in images, for retrieving distances and redshift of sources, and also to find possible relation between dark matter halos and their host galaxies. For my scope, that is to infer the mass of dark matter halo in real galaxies, there are a priori two crucial questions to do. The first one is how different galaxy physical properties correlate with dark matter halos. And if they correlate, which of them are good or even the best estimators for the mass of these dark matter halos? Of course, the most well-known, well-studied, and largely studied relation that links the galaxy to its halo is the stellar-to-halo mass relation that links directly the stellar mass to the dark matter halo mass. Another possible relation is that the galaxy size correlates with the size of the halo where it is hosted. However, in this kind of study, one should take into account also for all the other correlation that these properties may have with all the other several properties. For instance, in fact, we know that stellar mass is strictly related to the mass of the central supermassive black hole, or again, as I showed you before, with the stellar metallicity, or it shows a relation also with the gas metallicity, that again, in turn, show a correlation with star formation rate, and it was also found that the ratio between the black hole accretion rate and the star formation rate directly relate with the mass of dark matter halos. So at the end of this process, we end up with, as you can see, a very intricate and complex web of possible relation. And of course, machine learning can be a way, can be a silver bullet to shed light on these hidden patterns. The main goal of this project, so it would be to exploit these machine learning techniques that learn are trained model on the basis of cosmological simulation in order to derive a functional form able to be used on real galaxies for deriving their mass of dark matter halos using the physical properties that you observe in your observation, basically. In machine learning, we usually observe a sort of trade-off between two properties, the accuracy and the intelligibility. Among the most accurate machine learning techniques, we count, for instance, boosted trees, neural networks, random forest. Much less accurate, but very, very, very intelligible, so easily to be understood by the user that is using these methods. We have, for instance, linear or logistic regression. In between these two different classes of models, there is a family of models called generalized additive models. The good thing is that recently Microsoft Research released EBM. EBM, that is the explainable boosting machine, is a state-of-the-art machine learning method that, in the context of generalized additive models with pairwise interaction, that is at the same time as accurate as intelligible. EBM is fully included into InterpretML, that is a toolkit, a full library of machine learning methods classified on glass box models and black box models. But let's focus on what EBM does. This is a generalized additive model with pairwise interaction. So if you have your data set of observation, the quantity one would like to infer, that in my case would be, for instance, the mass of dark matter halos, can be expressed as a summation of two classes of functions, the one-dimensional and two-dimensional shape functions. Here in this two sketch with fj and fk, I'm indicating two of the n possible observables you have in your observation. For instance, I don't know, stellar mass, metallicity, colors, luminosity, and whatever. while the score on the y-axis or the colored map on the 2D shape function is a quantity in units of the quantity to be inferred, so the mass of dark matter, that the user has to add or subtract to make the final inference. But I will show you an example very soon. EBM is largely used in many different science fields. The first application was presented in Carlo et al. 2015 from the Microsoft research team to conduct a study for predicting the probability of dying because of contracting pneumonia. It was also used for conducting recently also studies on COVID-19 pandemic situation, but also for conducting psychological studies, for instance, for shed light on psychological hidden patterns on a catalog of serial killers. And in astrophysics, it was used also by Walmsley et al. In 2010 for understanding the role of non-morphological parameters in galaxies. For my first test, or for my first application of this method, I selected from Illustristin G100, from the redshift 0 of Illustristin G100, all the central galaxies with a total mass greater than 10 to the 11 solar masses. Meaning by total mass, the mass given by the sum of all the massive components, so the dark matter, stellar, black hole, and gas mass. And to retrieve the mass of dark matter, we used 7 properties so far. The stellar, gas, and black hole masses, the star formation rate and the black hole accretion rate, and the stellar and gas metallicity. The total sample I extracted from Illustristin G is composed by more than 15,000 central galaxies that I split into subsample. The 70% of the original sample is employed for training the model, and what the model learned is then tested on the 30% sample remaining. What EBM learned on this 70% sample? This is what EBM learned. This plot, the overall importance plot, is telling us which is the relative role in making the inference of the mass of dark matter halo given by the features that you are using, and also the pairwise interaction, the 3 most relevant pairwise interaction found by EBM, indicated here by the crosses. As you can see here, all these 10 terms are giving their important contribution for making the final inference of the mass of dark matter halos, right? But what I would like to highlight is that the baryonic components at redshift 0 is occupying the 3 most relevant positions in order: the gas mass, the stellar mass, and the black hole mass. And for instance, I would like to show how the 1D shape function of the stellar mass appears. Here, on the x-axis, you have the stellar mass range of your training sample, while on the y-axis, you have the score. Score equal to 0 correspond to the mean of the dark matter in your training sample, that in my case, as you can see here, corresponds to 10 to the 11.4 solar masses. How can I use, for instance, this 1D shape function for the stellar mass? Basically, this plot is telling me which is the role to the final inference given only by the stellar mass. And for instance, to the total contribution, to the total inference of all the properties used, a galaxy with a stellar mass of 10 to the 8 solar masses add a contribution of -0.1 to the total inference. Instead, a more massive system, for instance, 10 to the 11 solar masses, add a contribution of 0.4. The good thing of EBM, as you can see here, is that this function is not, for instance, a straight line or a knot function like a parabola or an exponential or a logarithm, but it's a much more complex function. And this much more complex function allows us to highlight peculiarities on the training sample we are using for training the model. For instance, here, around the 10 to the 11 solar masses, there is this transition. There is this hump-like structure. As I show you in the previous results, this hump-like structure can be explained in terms of the fact that above 10 to the 11 solar masses, as I already said, the extrastellar component becomes as relevant as the in situ component, or even more relevant than it. Anyway, our EBM model learned something by the trained sample, and so we can test what it learned on the test sample. And these are the predictions made for the test sample. On the x-axis, you have the mass for the test sample galaxies, directly derived from the simulation, from Illustrating. Instead, on the y-axis, you have the residual, so the difference between the mass predicted by EBM and the mass from the simulation. And as you can see here, EBM is fantastic in this sense because it found a distribution with a very, very tight scatter, smaller than 0.06 dex. And in this sense, EBM is a very promising tool because it allows to accurately provide an estimate of the mass of dark matter in this sense. But I did more than this. And for instance, I extended the analysis toward Eiger and Eiger redshift in TNG in order to understand if EBM is also capable to understand if the importance of given features change as a function of time. To do that in retrieving the mass of dark matter halos, of course. To do that, I analyzed also other snapshots from redshift 0 up to redshift 3. And for instance, here I show you the same plot of before, but for the overall importance plot, but for the redshift 3 snapshot. Here there are some differences. There are some new entry pairwise interaction. Some of the terms remained in the same position of the zeta-0 overall importance. For instance, the gas mass is again is lying on the first position again. But what I would like to show you is that while at redshift 0, the stellar mass and the black hole mass occupied the second and the third positions respectively, now at redshift 2, at redshift 3, the role of stellar mass and the black hole mass go down, while the star formation rate and black hole accretion rate go up. And this is a very good thing because EBM is also capable to trace this change in the evolution. And this is something that is expected from theory because we know that at Tiger redshift galaxies formed more and more stars than their counterpart in the present day universe, and also that the black hole accretion rate at Tiger redshift is much higher than also passed in passive galaxies today. So in conclusion, this is still a very ongoing project. It's a number. It is still in an embryonal stage. The aim of this work is to compare, is to train a model based on simulation, a cosmological simulation, for deriving a functional form for predicting the mass of dark matter halos in real galaxies. So far, we do find that EBM is a very promising tool because it finds a very high correlation between and provide a very good estimates for the mass of dark matter, finding that, for instance, the baryonic component like the mass, gas, and black hole masses are the three most relevant estimators for them. And the estimates of these dark matter halo masses are very accurate with a scatter lower than 0.06 dex. And it is also able to trace the evolution, the back-in-time evolution of the importance of the features used in your inference. What the future of this work? There is a very huge stuff of things to do. I'm going to extend my analysis adding other physical properties. I'm going to enlarge my sample, including galaxies from the larger simulation Illustrating G300. And since EBM is very promising tool, I think that it is very promising tool also for comparing and constraining the next next generation of semi-empirical models for understanding the mutual role between the dark matter halos and their host galaxies. And then going, for instance, to exploit mock galaxy catalogs derived from Empire or other semi-empirical models, for instance, the one developed by Rodriguez Puebla, by Aldo. And then the final aim would be to find a functional form to predict the mass of dark matter halos in real galaxies. So I want to leave you with my conclusion, and let me give you just the take-home message of these works I'm involved in. I find very evidence for the evolution of early type galaxies and confirm the previous evidence of the merger-driven evolution behind the early type galaxies. And also I'm studying the very intriguing field of the connection between dark matter halos and their host galaxies. I would like to underline the paramount need of exploiting state-of-the-art cutting-edge advanced statistical and machine learning methods for comparing observation and simulation in consistent ways, as consistent as possible at least, and also to handle this huge amount of data that are going to come from the next generation of surveys. I think that that's all. I'm open to your question, and thank you for listening to me.
Okay, thank you very much, Carlo, for this nice presentation. So, is there questions or comments for Carlo? Jorge?
Aldo, can you hear me?
Yes.
Okay. Thank you, Carlo, for the nice talk. I have a couple of questions regarding your results from the manga survey. I'm pretty sure I missed it, but you mentioned, well, you have a comparison between illustrious and the mass and the sample from manga, right? So you do this comparison between TNG and manga for redshift 0, right? Is that correct?
Yeah. Because manga, of course, lies in the redshift range in the present day universe below around the redshift 0, yes. So I did this comparison with the redshift snapshot from TNG 0.1. That is more or less the median redshift of the observation in the manga survey.
Yeah, exactly. That's what I was going through, because if you look at the mass redshift distribution of the manga, there is a significant, I mean, it was designed to be like that. A bias for massive galaxies tend to be at higher redshift in comparison to low mass galaxies. I'm pretty sure you know that. So I was wondering if you can have you quantify that bias that you observe, that it is this intrinsic bias from the manga sample. In order to compare with your illustrated simulations.
Yeah, basically, I haven't done it yet, in the sense that the aim of this work was properly to compare manga and TNG, so to provide a scenario of the present day universe galaxies. It's something that I will do in the future, of course. And this is something that I cited before, because I would like to reconstruct how individual galaxies in TNG evolve through cosmic time, and in this sense I can in order to explain how their physical properties evolve through cosmic time, and in this sense I can provide an answer to this question to understand if there is a bias that varies as a function of time.
Yeah,
but
I will encourage you to check that, because it's a significant difference in time if you have a low mass galaxy or a massive galaxy in manga. So that's something to consider about. The second question that I have is that you show a Radial profile between the simulations and the data that you use with the I think it's Firefly and Prospector.
Yeah.
I'm not I'm not surprised that you have a significant. I will be really surprised and concerned if you don't find a significant match between the observation of the stellar mass surface density profiles and those from illustrious. But you do seem to find discrepancies between the metallicity, the stellar metallicity, and the age, and the profiles. So can you comment on that, like those ones? Yeah. Can you comment on those differences?
Of course, the first thing that I would like to say a priori is that the reason why for these three quantities, metallicity, stellar surface density, and age, we decided to use two fitting code is the one that I said before. So the fact that stellar fitting codes can provide in real galaxies different estimates for the same galaxies about the same stellar physical property. At least for the metallicity, as you can see, in particular above 10 to the 11, at least the shape of these metallicity profiles are in enough good agreement, in particular above 10 to the 11.5 solar masses. But this match is not so good, as you was saying, below 10 to the 11. Because even if, although these are two outliers, because there are a few more points here, but at least there is here discrepancies of 0.2 dex in this direction in the stellar mass, and the situation is it's harder here for the age. Then one of the main reasons, of course, is resides in the receipt behind the implementation of illustrious TNG, because maybe the agent feedback inside these galaxies maybe can be too high in some kind of these systems, and so these discrepancies, I suppose that in future from the illustrious TNG team will be improved, because I think that basically is due to the receipt on how the physical implementation, the physics behind the formation and evolution of galaxies in TNG is implemented. I think that is something related to in particular to the effect of the agent feedback that may cause these systematically shift. The good thing again here is that at least the age profiles lies in between these two profiles of Firefly prospector, but here the situation is more critical than the stellar surface density, of course.
Yeah, exactly. So that could be, as you mentioned, like a combination of effects. No, on the one hand, you may have like the physics that you are injecting to the simulation, but on the other hand, as you can clearly see from this comparison between Firefly and Prospector, the differences in ages is of the order of almost 2 gigayears, right? So that's
2 to 3 gigayears. Yeah.
So it will be worth to explore what was causing this difference between the different single stellar population fitting techniques. Okay, that's great. Thank you for the nice work, Carlo.
Thank you very much.
Okay, so Silvia, Vladimir, and then Octavio.
Okay, my question is very simple. On the last section of the talk, you mentioned that there is a relation between, or the dominant diagnostics can be the gas of the mass, the gas of the stars, and the mass of the black hole to determine the mass of the dark matter. Now, what are the physics of that, and how come these changes for different Z? I mean, if you go to different Z, you have a different diagnostics, dominant diagnostics. What's the reason?
Yes.
I know that the mathematics is what you have, but I want to think about the physical reasons.
Yeah, I understand. Yes, of course, here at redshift 0, and it's not still valid at higher redshift, the gas the stellar and the black hole masses are the three best estimators. The explanation, the possible explanation for this is due strictly to, at least for the gas and the stellar mass, in terms of the baryonic component, the dynamical aspect, because in this galaxy, in these systems, the galaxies now are relaxed. So, dynamically speaking, stellar masses and gas mass are gravitationally bounded to the dark matter halos. So, I think that it's unavoidable to that these are the two best estimators. And of course, for instance, the stellar mass is the up to now through the stellar to halo mass relation is the I think that is the most well studied, the most well known relation, because it's very easy to be retrieved the stellar mass under some uncertainties, but it's something that is gravitationally bounded. So the origin is on this direction. The fact that dark matter halos, gas, and the stellar mass share the same dynamics through the cosmic time while the galaxies evolve. The fact that the black hole mass are strictly related can be due to several factors. One of these factors was the one that I showed you before when I, at the beginning of this part, because we know that, that the stellar mass directly is linked with the supermassive black hole through the Magorian relation. And so if there is this link between the stellar mass and the supermassive black hole mass, and there is the already link between the stellar mass and the halo mass, I think that also there is a hidden link between the black hole mass and the dark matter halo. So that is why at least at redshift 0, after all the physical processes occurred in these evolving systems, these are the three most relevant components.
You mentioned that for the frequency, the indicators were different parameters.
Yeah. I can go. Because at redshift 3, as I showed you before, for instance, the gas mass, because it's the second most dominant component in a galaxy, is the most dominant component is gravitationally bounded, and it remains in the first position. The fact that Tiger redshift, the stellar mass and the black hole mass go down can be due to the fact that these galaxies are still evolving and they are not in equilibrium, because I think that these galaxies are experiencing a lot of mergers, and so the mass is not well, the mass of stars is not well defined, in the sense that the galaxy is not at its last stage. It's not an equilibrium, and I think that it's something that I'm studying now in this period, conducting this work. But I think that the answer is behind this, is in this direction. The fact that these systems are still evolving.
Thank you. Thank you. Very nice talk.
Okay, Vladimir, Octavio, and finally Jesus.
Okay, thank you, Carlo, for your very nice presentation. I think you are studying very hot topics in the field, so hot and debatable that probably we are not in agreement with some of results, for example, regarding the role of dry mergers in the evolution of early type galaxies. In Lacerna et al. And in two papers that we are now preparing, we find that the role of dry mergers is not so relevant as probably you claim, but probably this is because we are focusing our study in the inner regions of these elliptical galaxies within 1.5 effective ready, and probably you and the Oyarzun et al. Papers are taking into account larger ready, where dry mergers, of course, are more relevant, yeah, in the growth of these galaxies.
Yeah.
So this was just a comment because it's a very debatable and hot topic.
Yeah, of course.
I have a question about the evolution of the velocity dispersion, stellar mass relation. I'm wondering if you consider that your results could be affected by biases typical of using surveys at different redshifts to infer galaxy evolutionary trends. For example, the progenitor bias. Do you know this? Are you taking into account this in your study?
Not so far. That is why, as I said before, I would like to conduct also a comparison between observation and simulation and to quantify how the effect of the progenitor bias also evolves through cosmic time. But what I can say is that in the final results that I show here, qualitatively speaking, I said you that from redshift 1, I suppose that this galaxy moves in this direction to reach the functional form at redshift 0. And according to works like Lopez San Juan, the progenitor bias should not affect so much below redshift 1. So, according to this work, what I can say is that at least for the fiducial sample, so as the SS and legacy galaxies that are which higher redshift that is at around the redshift 1, we should not have relevant effects on progenitor bias, but it's something that we already planned to analyze, making use of cosmological simulation, because there we can address this easier this question if a galaxy is still an early type galaxy at higher redshift or was, for instance, a star forming one.
Okay, thank you. And just a comment regarding the age profiles of the early type galaxies. Our results with Pipe 3D are in better agreement with prospectors, the result prospector that we showed. Just to
I drew. I written before. The prospector and Pipe 3D estimates are in agreement between them, at least for age. Yeah, of course.
Thank you.
Just a quick comment on this figure. Actually, I also don't believe that he's affected by a progenitor bias, because you also see something very similar with the simulations. When you plot the maximum circular velocity of the halos versus the halo mass, you see the same trend in the evolution, which is actually very encouraging.
Yeah.
Okay, that was my comment. Octavio?
Thanks, Alan.
Hi, Carlo. Very nice talk. Thank you for the presentation. Just a quick comment on the question. The quick comment is for manga, for example, capturing velocity anisotropy is hard. Also, I believe for simulations, for illustris, it's kind of difficult at the small scales to capture anisotropy. My question is, if that has an effect in your comparison. It's very good that you say that it's very hard to compare observations and simulations. I'm pleased to see the careful work, but I'm not sure if both of them capture that and if that has consequences for your comparison. This is just a comment. My question is regarding the last part of the talk. Very exciting. In my opinion, this is the future for these H-of-D techniques. And however, as any powerful toy, has to be used very careful. Probably you know the work of Calderon and Berlin. They try to do something similar with different techniques, XGBoost, random forest, neural networks. Do you believe you obtain the same results or different, and how dependent is from the method, the results for this assigning of total mass or halo mass to the galaxies? I guess this is one of the key things when, you know, there is currently an explosion of using these techniques for many things, photo C and many other properties of galaxies. Yes. What do you think? Do you believe your results are consistent with other applications? different, how dependent is from the method?
Okay, thanks, Octavio, for your question. Let me say before that this is the first time that I'm conducting a work both in the context of galaxy header connection and in machine learning application in astrophysics. And it is very rewarding, and it's opening my mind in this direction. I don't know the work you mentioned before, but what I can say in this direction is that, as I showed before, you mentioned, yeah, what?
No, sorry, okay. I don't know what happened. Okay. Continue.
Among the most accurate methods in machine learning, there are, as you say, the random forest or neural networks. What I would like to say is that with respect to these kind of very accurate models, EBM has comparable, this method has comparable performances in terms of accuracy, but it is very, very, very much more easy to be understood, because with random forest or neural network, you cannot have information like this, for instance, for the 1D shape function of stellar mass that I showed you before. And this is, I think, that is a very good thing, because through this shape function and through this method, EBM in general, you are able to understand what's going on in each sequence, in each individual features you are using, in my case, for instance, for retrieving the mass of dark matter. So yes, I think that one should take care in using these use these kind of methods, but I trust EBM. We are collaborating with the creators of EBM, that are the Microsoft Research, the researchers of Microsoft Research, Rich Caruana and the others. And I think that this method is very promising in this direction. So I don't know, sorry, I don't know this work that you mentioned, but it's something that I can look, if you can suggest me this reference later, it would be great.
By sure, I will send you more questions, and thank you for your explanation. It's very good.
Thank you.
Jesus, and the last question is for Jorge. Go ahead.
Yeah, actually, I'll be fast because the question was answered, but congratulations for your work. It's very nice, and your presentation. And yes, for me, was what already was asked by Vladimir, is the relevance between wet and dry mergers and its implication in the way that the mass sigma relation evolves. But it's already solved. So congratulations, Carlo.
Thank you very much. Thank you.
Jorge?
Yeah, thank you, Aldo. Another question for Carlo, sorry about that, but I'm having a hard time trying to understand. I mean, we know from the nearby universe that there are many relations, many parameters that correlate with the stellar mass. For example, you know that there is the star formation sequence, you know there is the mass metallicity relation, you know there is a strong relation between the gas mass and the stellar mass density. So, and the stellar mass, sorry, well, and the stellar mass density as well, spatially resolved relations. My question is, how do you disentangle somehow this strong relation that you observe in the local universe, at least, when you try to understand and when you try to derive this mass halo? And this is something that you just mentioned it in your presentation of this topic. Kretzi is also doing this in order to understand or derive the metallicity, the gas metallicity for galaxies, no? And that worries me because you know, there is a, let's call it cross relation. There's an interrelation between the stellar mass and many other properties. And my question is, again, how do you disentangle this different scaling relation that we observe in the local universe in this type of, let's say, predictions from the machine learning? How do you, account for that?
Okay, if I understood your comment, actually, do you mean if with this method I'm able also to reveal the possible cross-correlation between, for instance, the stellar mass and the other quantities to retrieve the mass of dark matter? Is it right?
So my question is, I mean, you know, that's, as you're showing in this slide, you're having many different calibre parameters in order to estimate your.
Yeah.
But for example, if you account for the stellar mass gas mass relation, right?
Yeah.
So in that case, what will be the primary driver? Will be the stellar mass or the gas mass? So that's my question. If you use the same machinery that you are using for estimate the mass halo.
Okay. Okay. The question is, this method works as the quantity you want to infer, the mass of dark matter halos. You can express it as a summation of the one-dimensional functions, the one that I just showed you, and also the possible pairwise interactions. What these pairwise interactions are. For instance, the three most relevant pairwise interactions at redshift 0 found by EBM are these three. Let's focus, for instance, on these on the central panel. We have on the y-axis the stellar mass and the gas mass, and we know, as you was saying, that there is still a 1D relation between the gas mass and the stellar mass. The next step, thanks to EBM, is that this that this relation that is still there between the stellar mass and stellar gas here can be visualized as a two-dimensional function. And for instance, here, as you can see, is colored as a function of the score that I mentioned to you before. In this case, the higher the mass, the lower the velocity, the lower the stellar mass, and vice versa. And it basically can understood this in the sense that if you have still more gas, it means that you are not still formed much stars. And on the contrary, if you have more stellar, higher stellar component, you have a lower stellar mass in this kind of systems. So we are still conceiving how to derive the functional form that in case would be a very much complex functional form, because as you can see, should take into account for n possible dimension, where n is the possible features and pairwise interaction you are taking into account. But also the existing relations between, for instance, the stellar mass and black hole mass, or the other relation, EBM is able to take into account for this existing relation in the total inference of the mass of dark matter.
And that's, so my final question will be, and taking into account, so the system, the machine learning knows that there is a relation between, that as you just mentioned, the mass gas and the stellar mass. So in knowing that, the machine learning predicts that the main driver for estimate the mass halo is the mass gas. That this the result you showed before. Is that still okay? I mean, that's still the case.
Yeah, but I mean, the plot I showed you before about the overall importance is telling which is just a rank, which is the best, the second best, the third best, the n best estimators for deriving the dark matter mass. But in any case, all these all these features, and also, for instance, the three most pairwise interaction are co-working together for inferring more well-constrained the mass of dark matter, for instance, with respect to an inference made only, I don't know, only considering the stellar mass. Because in this case, if I made the inference with this method only with the stellar mass, you have like the stellar to halo mass relation, right? On the X is the stellar mass, the Y is the mass of dark matter. But in this case, the function you are considering is a much more complex function that considering at the same time all these features that you are considering and all the n pairwise interaction, where n in this case is 3 because the user, me, set in this machine that I wanted to consider just the 3 most relevant pairwise interaction. I think that it's
it's more clear.
Okay,
Thank you,
it's
Carlo.
like a principal component analysis, but much more powerful and much more extensive. Yeah, something like
that.
But and much more easier to be understood, I think.
But the problem with that is something, and the reason that I mentioned this is because we are doing one of my PhD students, she's doing something very, very simple, which is quantifying precisely something like this, which is what is correlating the most with metallicity, stellar ionized gas metallicity in nearby galaxies. And you have like you're showing, you have that the star formation rate correlates, of course the stellar mass, many other parameters, the morphology and whatnot. But when you remove this relation between the gas metallicity and the total stellar mass, all these possible correlations vanish, basically. So you don't have any significant correlation between the metallicity, the residuals of the mass metallicity relation, we have to say, and the star formation rate. And this is the reason, that's what I'm asking you, because what we're finding is that when we remove the mass relation, the impact of the mass in the metallicity, we don't seem to find any other significant relation with any other parameter, like, for example, the star formation rate or the gas fraction or the mass of the gas. So this is to mention that it is necessary to consider the relation between the stellar mass and the other different parameters, like the star formation rate or the gas metallicity and so on. And well, having these powerful tools like machine learning, I think that, well, this will be a good job, but we shouldn't forget that there are secondary relations, so to speak, or intricate relation between mass and other parameters. So that's why my take.
I think the EBM takes into account that, and you can see here in this figure studies taking into account all the possible covariances between the galaxies.
Exactly, the covariances.
Okay.
Thank you, Carlo, again.
Thanks. Thank you very much, Carlo. I think this is a very good talk. And let's clap, Claudio.
Bravo. Thank you.
Okay.
Thank you.
Thank you so much.